Welcome, everybody. I want to start with saying that I'm incredibly proud to speak here today. I can still remember the first Kotlin conference in San Francisco. That was like maybe, I don't know, 1/10 of the number of attendees. And I've always been a great fan of Kotlin right from the start. And it's amazing to see so many other people having the same sense that this is a fantastic and great language. However, what I want to talk about today is not about the past, but about the future. So how will the future of programming look like? And if it's up to me, it won't be Kotlin. It will use Kotlin, but it won't be Kotlin. So here's my view of the future. Let's look here on your right. That's the current stack. So we have different CPUs. And then on top of that, we have an abstraction layer that kind of allows you to write once, run anywhere. And then we have a programming language, a bunch of libraries that you can reuse. And that's how we develop code. What I'm going to talk about today is the thing that you see on your right. And this is a virtual machine that uses LLMs as its CPUs. So there's a bunch of models that corresponds to CPUs. And then there's a neural virtual machine that abstracts from these different models. So you could say prompt once, run anywhere. And then there's a new programming language that I'm going to show you today that will be the language in which you can write code for this new neural computer. And then, of course, there's a repository for sharing code as well. And the nice thing is that I think there's way more people that could write code in this new world than there's in the old world. Here's another way to look at that. And why do I say that developers are going to go away? Well, in some sense, developers, we are just the middleman between the user and the computer. The user, that's ultimately why we write code, right? It's the user has some problem that they want to solve. And it just happens to be that our current languages, even though Kotlin is amazing, they're kind of hard to use, and that's why we need developers to write code. But with AI, now the end user can write code themselves. Now, of course, you can say, oh, but Erik, we have been telling this story forever. Everybody is trying to do this. Visual Basic tried to do that. Everything tries to do. 4th generation languages. But I do think that with the current generation of LLMs, we definitely have a phase change, and things have changed, and now this is possible. Now let's look at a concrete example. Here's a slightly convoluted question. It looks simple, but if you think about it for a bit, it's not completely trivial. So how much Bitcoin do I get from selling 1 kilogram of gold, and how many Microsoft stock can I buy with the proceeds? Now let's ask ChatGPT to solve this. And it starts off nice, saying oh, I need to go through these steps, find the price of gold, find the price of Bitcoin, etc. And then it's starting to do a calculation. But maybe, I think ChatGPT has been to a party and has not sobered up yet, because all the answers that it's giving, or all the numbers that it's using, are completely wrong. Even though the computations look right, the numbers are completely wrong. And then in the end, it tells me, here's the answers, but make sure to check that they're valid. And this is a complete nonsense, right? Because I asked this AI to do something for me, and then it tells me in the end, Erik, you have to do it yourself anyways. So that's completely useless. So now let's look at how I envision this. And this is like this. As I said, this virtual machine is called AutoMind. And here is the question. So I asked the question, and now what happens is that the model generates a program in this new programming language. So this new programming language is literally kind of a form of literate programming. So it's natural language text, and then in between the square brackets are snippets of code. And so hopefully anybody that can write an Excel spreadsheet should be able to read this code. Later in the talk, I will kind of like do some common bike shedding, why the syntax looks like this. But for now, I think it's just look at it. It's like anybody that if you have ever done a little bit of spreadsheet programming, you should be able to understand this code. All right, now if you think about it, if you look at that last computation math, GB times B divided by M, and you look at the kind of like step 3 there, you see that there's G divided by B, that's GB. So it's a little bit too complicated. And just like with regular code, if a program in this new programming language looks a little bit complicated, we can refactor it. But of course, we refactor it by asking a question in natural language. So you can refactor it by saying, can you simplify the calculation of that variable? And then it's so friendly, it says, like, of course, let me just refactor it for you. And now you get a much simpler program. Now, of course, I asked how much Bitcoin do I get from selling 1 kilogram of gold. That's not super useful. So let's abstract from this 1 kilogram of gold to X kilograms of gold. So now literally here, I've defined a function. That function has a parameter X, but the function definition or the body, or sorry, the header of the function is just natural language with this kind of like formal parameter in there. And now the model, again, generates the implementation of this function for us. So this is a literally executable code in this programming language that hopefully everybody should be able to do. And now, again, maybe I want to refactor this a little bit because the explanation is a little bit too terse. So I can ask the model, can you kind of like, explain this a little bit better? And again, like it refactors this by giving me some more details. All right, now if I rip out all the natural language, I leave the square brackets, then the program that it generates, and I give it a name, so that was this function that takes an X, and I give the two result variables there, bx and bm. Now, if you have ever done logic programming, this looks like a weird form of Prolog. So the extracted code that's hidden in this programming language is really logic programming, which is interesting because in the 80s, when the old school people were doing AI, they thought like Prolog is the language for AI. And so what I've kind of done is I've reinvented Prolog, but now I'm using LLMs as the runtime and Prolog as the programming language. So the cycle is now kind of perfect again. But let's look a little bit at history, because as I think this was Churchill, but it's attributed to a lot of people. If you don't learn from history, you're doomed to fail. In the 17th century, Leibniz, that's the person that invented binary numbers, calculus, differentiation, so all the things that allow machine learning to happen today, he was already thinking about this idea of automating things, but he was kind of like skeptical that machines could be intelligent. And I have that same opinion. I think this whole notion of talking about artificial intelligence is wasting time. I often compare it to asking the question if a submarine can swim. Well, I don't care if a submarine can swim or not, if you want to call it swimming or not. Submarine can stay underwater longer than a human. It can do useful things. So I don't really care if that's called swimming. The same thing with AI. I don't care if this thing is intelligence or whatever. As long as it's useful and it can generate code for me, I'm happy. So I'm not going to take this bait about like, oh, is this intelligent? Are these machines going to go after us and kill us? I don't think. I think they're just like washing machines. They just are machines that are doing useful stuff for us. But that's not like a unique proposition. If you look at Turing, for example, he did believe that machines could think. That's why he came up with the Turing test. And another common error that we seem to make is that we think it's all easy, right? In 1958, that was way before you all were born. Like some of these ML researchers thought, oh, if we lock ourselves up for a few weeks in a room, we can solve the problem of AI. Famous last words. And then, of course, in the 80s, the fifth generation project would like revolutionize offices. It would like automate all the work. It took a little longer than that, but I do think that we're finally getting there. Now, in the 80s, I was doing my PhD thesis, and there I was using category theory and transformers. Very different kind of transformers, but never mind. And nobody thought that category theory was any useful. But right now, apparently, if you're doing category theory, you can get lots of millions of dollars, even though the venture capitalists don't even understand what you're doing, but it looks cool. So if you do category theory, now finally you can start making money from math. And as I said, with the advent of these large language models, there's a lot of AI doomers, but I'm not a doomer. So I'm an optimist. All right, let's now dive in a little bit more in what's going on behind the background. And let me show you a slightly simpler question. And as you know, the Netherlands, where I'm originally from, is all below sea level. So for Dutch people, it's very important to know what the water levels are, and especially the water levels in the rivers, because if that's too high, then the country floods also from the other side, not only from the sea, but also from the other side. Now, in the past, what you would do is you would go to a relational database, you would get a beautiful table, and then you would ask a data scientist, can you please write a query that gives me the maximum level, water level over time? And they would go to their office, drink a lot of coffee, and turn that into this SQL query. Now notice, even though SQL uses English keywords, it's far from a natural language, and it's a really hard language. And this is what I mean by us developers standing in between the end user and the computer. The end user has a really simple question. What was the highest water level ever recorded at low bit? And now they need some data scientists to write this kind of freaking crazy SQL language that I don't think anybody really understands to get the answer. So yeah, I think this is a bad state where we're in. And we shouldn't be satisfied with that. We should be wanting to improve from this state. Now let's ask ChatGPT, what's the highest water level ever recorded in low bit? And it will tell you the answer. And I think this answer is actually correct. But also, don't be fooled, because you think that this is English, but it's not really English. What it's just a sequence of tokens, and I can remove some of these tokens and get something that doesn't even is grammatically correct. And when I ask that question to ChatGPT, it will still give me the answer. So it looks like you're talking in this thing in English, but that's not at all the case. It's just working at the level of tokens. In some sense, that's the... Is this... maybe somebody is some Luddite, like in the olden days, is setting the building on fire to go against AI. Oh, is there really a fire alarm? Okay. Well, thank you everybody for remaining calm. This was actually a good exercise. I was in the gym this morning and I didn't see a lot of you there. And I do think that if AI will take over more of our jobs, it means that we have more time to exercise and go to the gym. So this is like a little preview of that live. All right, let's I continue where I'm going. I was kept like talking about asking ChatGPT about what was the highest water level ever recorded in Lobit, and it could answer that question based on the knowledge that was encoded in its weights. And so this is like one mental model that people have of LLMs, namely that it's a database of compressed world knowledge. So just as a relational database stores its knowledge into rows and columns, an LLM stores its knowledge into weights. These weights get there by training and fine-tuning, and then you can give it a question and it gives you an answer. So let's get if it's an Erik Meijer talk, there should be some math. So let's look at some math now. So what if LLMs are like a database, they must have a query engine, right? Because the database has a query engine. So the query engine of an LLM is the next token prediction function. And this is the signature. So next takes a sequence of tokens, the input context, and it returns a probability distribution of tokens. And a probability distribution, I'll show later, like a concrete example, that's this kind of weird P. But of course, if I give you a sequence of tokens and it gives me one token back, that's not very useful. So what you need to do is you need to extend this one token prediction to multiple token prediction, and that's this next function. So that next function takes a sequence of tokens and returns you a probability distribution of more than one token. And what is a probability distribution? It's just a non-deterministic choice of possibilities where each possibility has a probability associated with it. For now, for this talk, let's forget about these probabilities and just say that whenever the model kind of predicts the next token, it can make a choice out of like a set of tokens, and it will make a non-deterministic choice. All right. So here is the way that I like to think about LLMs, how they kind of operate. And this is using big step operational semantics. If you're a real language geek, you probably know what a big step operational semantics is. Who knows what a big step operational semantics is? No, a few hands. Good. Now you're not so unique anymore because after this talk, everybody will know what a big step operational semantics is. So let's look at how to read this. So the first rule says, if I have a question, then the LLM can decide to stop generating more tokens. Is it at some point, when you ask a question to ChatGPT, it will stop, right? It won't talk infinitely long. So if I ask it a question, at some point it may decide to stop. The other possibility is I ask it a question, then it uses this next relation to generate the next token. That's what you see, Q, down arrow, next, T. So it non-deterministically creates a token. Then it puts that token to the input, and it recursively calls the LLM to generate an answer. And then the result is, the answer for Q is the next token in front of the result of that recursive call. Right? So this is just a recursive generation of tokens. And these AI folks, they like expensive words just to confuse you even more. And they call it auto-regressively. But auto-regressively just means recursively extend a sequence and kind of feed it to itself. And that's what you see here, right? Like I feed this sequence, the Q is fed into the LLM to get the answer. And I do that by feeding a longer sentence into the LLM recursively. So that is what when people talk about auto-regressive generation. It's just like recursion. All right, now let's look at a slightly different question. What is the current water level in Lobit? And this is a question that the model cannot answer because that's not stored in its weights. Because the weights were that's based on training data, and at some point the training of the model has stopped, and so it doesn't have current information. So you can ask the model, what is your cutoff date? a few months ago, that was January 2022. This one is December 2023. But obviously, it doesn't know the current water level in Lobit because it only knows what's in its weights. Now, often it might hallucinate, just like what you saw in the previous question when it kind of just made up the current price of gold. And how can you fix that? Well, you can give that information, that dynamic information, you can feed that to the model explicitly. So here, I feed it the current water level. I get that from some web service. I paste that into the query, and then I ask the model to answer it. And here I do a slightly different trick as well. I also ask it not like what the water level is at Lobit, but I ask it what's the water level where the river Rhine enters the Netherlands. So that is knowledge that is encoded in its weight. So now it's using two sources of knowledge. It uses the knowledge that I provide explicitly in the context, and it uses knowledge that's encoded in its weights. And then it's kind of quite nice to tell me, based on the information you provided, the water level is this, and then it knows that where the river Rhine enters the Netherlands, that's Lobit. So it's using these two forms of knowledge, which I think is pretty nice, right? One in green comes from the weights, and the stuff in blue comes from the context. And this is called retrieval augmented generation. I guess more people know about retrieval augmented generation than about big step operational semantics, which maybe is a little bit strange for a programming language audience, but I guess that's the way it is. But what RAG does is it takes the prompt, uses that to get relevant information, and passes that with the prompt to the LLM to get the answer. So if we take a little step back and look at this picture here, we see that we have an infinite storage of knowledge, and we chunk that up in little snippets. And then whenever we ask a question, we need to find in that infinite storage the information that's relevant for this query and then pass that into the finite context. But one way to look at RAG is that we give the model an infinite amount of knowledge. And the things that is encoded in the weights, it's like the read-only memory. The context is like the RAM, random access memory, and then we can bring in stuff from the secondary storage into the context, the finite context. And guess what? That's exactly what virtual memory is. Virtual memory, your computer has a finite amount of RAM. You want to give it the illusion that it has an infinite amount of RAM, and then the virtual memory system swaps in the relevant pages from secondary storage such that your computer has the illusion of an infinite memory, which is exactly what RAG does. So RAG is nothing more than virtual memory for neural computers. And here you see them side by side. Now let's have a little fun to show how RAG is implemented. And let's look at our favorite function, equals and hash code. Probably if you have ever interviewed at some crazy company, you get some coding question about equals and hash code. If you use Kotlin data classes, that's great because then equals and hash code are implemented for you. And the reason is that there's a lot of restrictions on equals and hash code. Like equal objects always must have the same hash code, but even if you have objects that are not equal, their hash codes might be the same. And so hash code is not a very useful function if you want to make it cheap to do equality. Imagine that I don't want to deal with equality, but maybe I can use get hash code to define equality, but that doesn't work. So if I have two objects for which equals is very hard to define, I cannot use hash code to implement equality. Now, one thing I mentioned when I was kind of continuing this lecture outside is that a lot of computer scientists are kind of uneasy with probability distributions and uncertainty. because they like kind of like equality, right? Because now I know these two objects are equal. And so if or not equal. So if I ask equals, it returns true or false. But just relax a little bit, take a step back, and let's think about it. Sometimes we don't want to know whether two objects are equal or not equal. We want to know if they're similar, right? That's good enough. We don't need to know true or false. We just need to know, are they kind of close enough? And especially when we're talking about things where equality is hard to define. Like, are these two pieces of code like equal? We can define like, oh, they give the same answer, but that doesn't capture the equality of the code, because this code might be beautiful, that code might be ugly. So even for code, like, we cannot define what equals really means. So let's loosen that up a little bit and say, can we talk about being similar? Now, LLMs give us like a nice trick to do some magic. So say that I have like, some complicated objects here, and I have to define equality or similarity between them. And that's really hard. So what I can do now is I can take some form of hash code and map them into this sequence of numbers, not just one number like hash code, but a sequence of numbers. And it's quite easy to define when two sequences of numbers are similar. All right? And this magic function has the property that if the hash codes are similar, then the objects are also similar. And that's kind of like, what we are using here. And this is what people call vector embeddings. So vector embeddings are just something like hash code, but that map similar objects to similar hash codes. And then you can use it to define similarity in an easy way. And then what is a vector store? Well, a vector store is just something where you give it a vector and it gives to you back the k vectors that are most similar. There's nothing like special about that. Now, let's use this vector store now to implement this notion of rag. So I had my prompt, and what I said is I needed to find all the chunks that were most similar to that. So if I write this code here, fetch all the chunks that are most similar to the prompt, then really what I do is I should get a type error, because the chunks are answers where the prompt is a question. So now I try to find all the chunks in the vector store, which are answers, and I find the ones that are most similar to my question. That's wrong, because answers and questions are like semantically different. So what I need to do is I need to map my question to an answer. And how do you do that? Well, I can just hallucinate an answer. So given the prompt, I hallucinate an answer, and then I look up all the chunks that are similar to that hallucinated answer, and then I use those chunks to answer my previous question. Now, this is called hide. People write papers about this in the AI community, where we as developers would say, like, have you ever written a paper about fixing a type error? But again, like looking at these things using a programming language or traditional computer science point of view, you can reinvent a lot of the tricks that the AI community comes up with and thinks are novel. But really, this notion of hide is just fixing type errors. All right, let's continue. As I said, like the model behaves like a database, but the database is typically a closed world. You give it a query, it gives you an answer, but it can only use the knowledge that's inside this database to come to the answer. And we have extended that with the knowledge from the vector store, but still it cannot do anything, any computations. It cannot look things up. It cannot send an SMS and so on. So for that, we need to give the model the ability to do computations. And computations or functions, and now I'm not talking about Haskell functions, sorry guys. I'm talking about real functions that have side effects, that can do anything, that can go out and, like pull the fire alarm. And so they have like an open world, and we need to give the model the ability to do that as well. And this is what is called function calling or tool use. So in that case, the model will suggest itself, it's trained to ask if it wants to answer a question to use certain tools. And in my case, these tools are Kotlin functions. And there has been a little bit of a standard that has arisen around function calls. This is the OpenAI function calling. Anthropic is using the same mechanism. Mistral is using the same mechanism. So this is a standard of how models invoke functions. And let's give you, again, an operational semantics for this. Because you can read like 10 pages of documentation, or you can read 1 page of operational semantics. So let's look here. So if I have a question and I want the answer, so that's what's below the horizontal line, question, down arrow, answer. So given a question, how do I find an answer? Well, the first possibility might be that the LLM, and I'm using assistant here to make clear that it's the LLM's answer. The question, the answer that the LLM gives me is just the answer. So there's no function call, so I'm done. Okay, so this is the first one. Everybody clear? If I can if the LLM can answer my question without function calls, I'm done. Otherwise, if the LLM tells me to call a function, that's what you see here. So the LLM answers with, call this function f with parameters e. Then I use the Kotlin interpreter to find the value of f of e and say that's x. Then I tell the model, here, the result of executing f of e was x, and then it finds me the answer recursively, and that's the answer that I give you. Right? So again, here's like recursively just answering this question by doing tool use. And here's an example. If I give it a tool, like find the water level in a certain place, you see that first the assistant tells me to execute this function, water level at low bit. I execute the function, and then it can answer the question to me. And then the next thing is it has answered the question. Now let's take a step back and look at what this function calling is. If you look at a regular computer, a regular CPU, it has an ALU that has all the primitive actions that the computer can do. It has RAM. We already showed that RAM corresponds to rag. And then there's a branch predictor in the computer, in the CPU, that tells you, given the instructions executed so far, this is the next instruction that you should execute. And then the control unit coordinates all that. Now let's look at how that corresponds to our neural computer. So our neural computer has tools. These are the primitive functions that it can call. And then, if you look at this LLM, really what it's doing, given the instructions executed so far, Q, it will tell us what is the next instruction to call, what's the next function to call. So LLM is literally like a branch predictor in a traditional CPU. And then we need a control unit, and let's give that a fancy name. Let's call that a reasoning engine. So I think this is quite beautiful, right? Like the architecture of this neural computer is exactly the same as the architecture of a traditional computer. But life is not always that great. And sometimes these models, if I'm using the model to predict the next instruction, it can do crazy things. So for example, if my tool returns that the water level is 1,100 meters above normal, the model will say, 1,100 meters, that sounds unusual. And it will then just ignore the value that came from the tool and substitute its own value. And that's really bad. So if the model is going to interpret the values that flow between the tools and the computer, then you cannot build a reliable system. So I don't care about non-determinism, but the model should get, like if I call a tool, it should get, like accept the value and not try to do anything with it. And this is the problem. So the model, the LLM here on the left, can observe the values that flow between it and the tools. Now, how do we solve this in a traditional computer? In the traditional computer, we have registers. So that we have values and registers. And when we call the add instruction, we don't say add 5 plus 2, but we say add register 3 plus register 6 and put the result in register 1. And so we hide, in some sense, the actual values to the branch predictor, because the branch predictor only sees the register names. So let's do the same thing here in our neural computer. And instead of showing the values to the LLM, we only show the names of variables to it. And in this case, the operational semantics looks like this. I'm not going to bore you with it, but what you see here is that when you execute a tool, I'm updating the environment, which binds variables to values, and you don't return a value to the model, right? Because you're only executing this code for a side effect. And in my implementation, this actually used the KotlinScript engine. And the KotlinScript engine, when you execute a Kotlin statement, it mutates the script engine to get, like, to when you make assignments to variables, but it might not return a value, right? Because it just does side effects. Now, just as humans, the model gets confused when you run a function with side effects and you don't tell it what happened. You only told it, well, this thing executed, but you don't tell it the values. And this doesn't work really well. So traditional function calls, that is the standard. You cannot make progress if you want to hide the values from the model. So we have to go back to the drawing table. And the way it does work is to go and look at something that people did before LLMs added function calls to them. And this is something called React. This is not React, the UI framework. This is the React, the LLM framework. And it has, in this case, has nothing to do with React. But what React does is it pushes the model through this cycle of an explanation. Then, based on that explanation, the model suggests to call a tool, and then it observes the result of that tool. And that tool, that's the thing in bold here, that again is done externally to the model. So the model thinks for a bit, says, I need to call this tool. You call that tool, and then you give the result to the model. And you cycle through that thing until the question is answered. Again, like that looks very much like a control unit inside a CPU. And here's how that works. So let's just look at this in this picture. So the dot, dot, dots, that's like the explanation, the thinking. That's the natural language part. And I'm going to abstract from that. But what the model does when it suggests an action, it suggests call function f with a. And then it hallucinates the whole rest of the program, right? Everything in yellow here is completely hallucinated. And you see that in its hallucination, it kind of like suggests to call another function f, and then call the result w, and so it will kind of hallucinate the whole execution here. And this is what people call chain of thought. So it is like this chain of thoughts with kind of like function calls in the middle. Now what we do, instead of like letting the model hallucinate, we intercept at this point. So we stop the next token prediction of the model. We execute that function, and then we give the value, and then we resume there. And then the model kind of continues until it suggests the next function. We intercept it, we execute it, we give it the value, and so on. Right? Is that clear? So we kind of like, we push the model forward. And this is actually, if you think about it, this is continuation passing style. We're kind of like implementing this, like, interception using continuation passing style, where this is the continuation. The thing in yellow is literally a continuation. except that it's a hallucinated continuation. And here's the operational semantics. And now what we do, instead of letting the model return or like reason in terms of values, we let it reason in terms of variables. So when it hallucinates a function call, it will tell us, assign the result of that function call to the variable called x. And then when it asks us to call f again or some other function, it says, assign the result of that call to the variable y. And I'm using this weird @ sign to distinguish between variable names and values. Now, why do I use this kind of like, function call, arrow, variable name? And the reason is that it's kind of weird how like Kotlin syntax is, right? If you define a function, you say function f takes an x, and it returns a string. So that goes left to right. But then when you call the function, suddenly it goes right to left. The thing on the left is the result of the function, which is on the right in the function in the signature. Where the thing here on the bottom, the result of calling the function is on the right, just like the type suggests. And this is much easier for the model because the model generates tokens from left to right. And so you don't want to have this inversion. And maybe for humans, that's okay. You read from right to left and left to right, but the model has to generate things flowing from right to left. So that's why this weird notation, but it's more consistent actually with the actual signature. All right, but when we do that, there's a very subtle difference. Instead of intercepting at the arrow, we now have to intercept at the closing bracket because we need to know the variable name that the model wants to use to assign the value to. So that's a subtle difference in the implementation. Again, here's the operational semantics. I will skip that. But let me not skip it. Let me not skip it because there's an important thing here, nothing to do with this particular one. But if you look at this operational semantics, and don't try to understand it, but what is written here doesn't tell you what happens when something goes wrong. So the operational semantics only gives you rules for the happy path when something is okay. But now imagine that the execution here of this script fails. Then this rule doesn't apply because the rule only talks about when it succeeds. And the same thing here, right? When it succeeds. So when it fails, how do you deal with that? Well, in practice, what you do is if something fails, you backtrack and you try another rule. And if that fails, you backtrack and you try another rule. So the operational semantics abstracts from that, but the implementation of the operational semantics uses backtracking to do that. All right. Let's take a little pause here and investigate what we have seen so far. So we have seen traditional computer has RAM, our neural computer has context. Traditional computer has virtual memory, our neural computer has rack, traditional computer has an ALU, neural computer has tools. We have branch predictor, LLM, and the control unit was a reasoning engine. Now we have talked a little bit about this programming language that we used, but of course, just like a traditional computer has a programming language in which you get like write code, this neural computer needs a programming language as well. So let's use the last 10 minutes to talk about like how do we design or how do we come up with a programming language for this neural computer. Now, if you have ever done like something with LLMs and you're prompting, you have noticed like, oh, you have to kind of like use this kind of like begging, right? You must return, and it's extremely important. You kind of scream at it. I don't think that that's a very pleasant way for humans to communicate with computers. And what we need is a language where we can kind of like, talk with this computer to like melt our minds, right? I want to kind of like explain what I want to the computer or to the AI, and the AI wants to explain to me what I want. And in the 80s, people thought that was Prolog. And turns out that the language that I ended up with is very close to Prolog as well. And as I mentioned way before, Leibniz in 1670 or something also envisioned a programming language similar to this. Now, let's kind of like, derive a programming language for neural computers. There's this philosophy, it's called the language of thought, that says, you don't need to read all this, you can, of course, look it up later, but it says that the theory states that thought, like language, has syntax. So if we want to kind of, if we kind of imagine how does the model think, and again, like I don't think the model thinks, but just let's pretend that the model can think, what would be the syntax of those thoughts? And what we have seen is that it was a chain of thought, right? There was some explanation, then it told us to call this function and assign that to variable x. Then it did some thinking and told us to call function g and assign the value to y. So really, what we observe, what the language kind of shows us to do, that is really one way that we can imagine that is how the model thinks. So the model thinks using chain of thought. So if we just make that into the syntax, we externalize the internal thinking in the syntax, then this chain of thought becomes a goal that we know from logic programming. It's a goal from logic programming with slightly different syntax. It has like natural language in between. And instead of having logic variables, it has like slightly different notion of variables, but otherwise it's very similar. Now, I don't know here if people heard about Tennant's principles of language design, which says that every syntactic construct in the language, you should be able to give it a name. So if I have a chain of thought, Tennant says I should be able to give a name to that chain of thought. And then the other principle that Tennant has is that if I have something that has a name, I should be able to parameterize on it. So I have to be able to give it parameters. Think in Kotlin, if you have a sequence of statements, what is a function? It's just a name for that sequence of statements. And then that sequence of statements might have parameters that I can then like call it with different values. And this morning, we saw the new language thing where inside a let, you can do break and continue. That's literally where you kind of say, this is a sequence of statements, and since I cannot escape it, I can use it kind of like right in place. So it's using kind of Tennant's principle as well. So if you give a name and parameters to these chain of thoughts, then you get a rule that looks very much like a Prolog rule. So in some sense, we have done nothing to invent this language. We have just observed how the model thinks, and then used Tennant's principles of language design to come up with the language. And then what are tools? The primitive tools, these are facts. So these are things that are implemented externally. And in this case, all the facts are implemented externally in Kotlin. And so here's an example of a program in this language. The user writes a natural language prompt. The assistant generates the program. And then you can give it a name and reuse it like that. So this is the way you kind of program with it. You ask it a question, it gives you an answer. You give that answer a name, you parameterize it, and that's it. All right, now since we have a bunch of like developers here, we always like to talk about syntax. Why do we use the syntax? So let's do some bike shedding here and see why this syntax is like a little bit weird like that. Ideally, what I would like is to just use Markdown as the syntax of this language. Except that with Markdown, the opening quotes and the closing quotes are the same. And I need to intercept, remember I needed to intercept the model from generating this thing. And if the opening and closing quotes are the same, there's nothing I can intercept on. So this doesn't work. So that's why I have the weird square brackets to delimit code, because I need the opening bracket to be different than the closing bracket. Then there's a whole bunch of other choices you can do, like Haskell has this thing called bird tracks. Don't like them. You can use HTML code, or you can use LaTeX. But none of that is better, so I stick with these weird square braces. Now you might ask yourself, Erik, why do you do this weird arrow with @signs? Why don't you just use Kotlin statements? Now the reason is that these functions can be non-deterministic. So if I'm calling like an external tool, it might not be a function. It might give me different answers. So for example, it's like in Prolog when you have this child clause, and Mallory is a child of both Alice and Bob. So if I call the function parent of a child, it can give me two answers. So it's a non-deterministic choice. So using regular function syntax like Kotlin doesn't feel right because these things are not functions. They can have like different answers. So that one was out. Now why don't use logic variables? In Prolog, you can do cute things. I can define how to concatenate two lists. And then I can ask, given this list, how do I split it into two other lists? So you can run these predicates in Prolog in reverse order. If anybody here has ever done Prolog, they always show this example, but then in practice, for anything more complicated, it doesn't work. So it's cute, but it doesn't work. And in this case, if you look at speech and speech to text, that looks cute, right? If I give you speech, you can give me text, and if I can give you text, you can give me speech. So this is one example where things can like go back and forth. But if I ask you, here's the city, give me the weather, that works. But if I give you the weather and tell you, give me the city, well, there's a lot of cities that have the same weather. So that would be way too many to one. And that's why I use this like left to right syntax, and I don't allow logic variables because it's cute, but it's not good in practice. And then the last thing you can say, Erik, what is this thing with this @sign that looks so ugly? Well, I think Python doesn't have variable decorations, but they can be anything. I don't like that. PHP uses $signs. I've been at Facebook too long. They have like hack, which is PHP. I don't like the $signs. Prolog uses uppercase identifiers for variables. I think that's also not that great. In Excel, you can have structured references where you can like refer to rows and columns using the names instead of like cell numbers, and they use @signs. So that's what I picked. So it's just pragmatic choice. All right, and of course, I'm not the only one that's looking at kind of programming languages for LLMs. Maybe the most interesting one is Dispy. And this is more like an optimizing compiler. So what they do is they kind of like try to optimize your prompts using all kind of optimization techniques, where I'm just more like a very simple JIT. I could use Dispy under the covers to optimize the code, but right now I don't think it's necessary. All right, with 3 minutes to spare, hopefully I've convinced you that we can build this neural computer and that everything looks very similar to the things on the left, and that it actually also uses the things on the left. So the future is not just neural computers, it's neural computers combined with traditional computers. But what I think is quite elegant is that the whole architecture and the whole stack looks very similar. And hopefully this new programming language is actually accessible to more people than just the like, whatever, 30 million developers that are around. And now we can empower the end users to solve their problems directly without needing a developer in the middle. I don't know if there's maybe time for a few questions. But anyway, and just to say, why is this at the Kotlin conference? Because everything is written in Kotlin, implemented in Kotlin, and it uses these kind of like the scripts, the tools are all done by kind of like executing Kotlin. So this whole neural computer actually runs on top of Kotlin. So Kotlin is the actual engine that glues everything together. All right.
Before the questions, sorry, can I have a small announcement? I want to make a small announcement. The whole schedule is postponed by 30 minutes. The next talk starts 2:30. That's all. And the schedule should be on the site.
And what about the party? The party starts at the announced time?
We'll see, we'll see. And still time for the questions.
Well, is there a question there? It's all up and running, but right now I don't have it available externally. I first need to find funding to make it generally available. There will be a paper about this soon. That's nearly ready. But yeah, unfortunately, there's only a few people that can play with it for now. But it's not vaporware. I can show you. I can give you a demo on my laptop if you want to see it. And the slides, way in the beginning. Love this. I went through 110 slides in 45 minutes. That's pretty good. But this is all this is done by the live system, so it actually runs. It's
how much power would it need to run in large scale enterprises in the future if it's adopted? How much power would it use compared to?
And you mean in terms of electricity or something?
Yeah.
Yeah. Well.
Or computing.
Yeah, compute. So what I'm using here is that the model actually, the AI part is actually the least bit of it, because the generation of the program is pretty fast, and then most of the computation is actually still just done in the square bracket. That's where most of the work happens, and the model just really generates the code, but then the execution of the code is the most part. So I would say it's similar to just running a Kotlin program directly, and the generation, the AI part is pretty fast. So remember, right? I'm not using the AI to do computations. I'm really using the AI only to generate the program, to JIT the code, and then I run the code.
Thank you.
All right, I think we're out of time. I will be here to answer more questions, show you demos. But thank you so much.